Okay, Assalamualaikum and hi guys. So again, we go to chapter 1, but this time is part 3. So I will continue on synthesizing the rate law. Okay, so how to synthesize the rate law? Okay, these are the algorithm how to synthesize a rate law for a heterogeneous reaction, which involve solid catalyst. Um, so these are the most important part in this chapter. So before you wanted to derive a rate law for a solid catalyst reaction. Okay, these are the steps that you need to follow. Okay, the first one is select a mechanism. Second, assume a rate limiting step. I have explained to you in last week lecture what is a rate limiting step, which is also known as rate determining step, RDS. And then the third step is to find the expression for concentration of the adsorbed species. So concentration stands for C, right? And then I is the species. For example, if the reactant is A and then produce product B, so the species involved are A and B. S is actually the catalyst active site. So AS, right? So I'll give you an example later and elaboration later on this. Okay, then the fourth step is to write a site balance and then derive the rate law. Okay, so finally you compare your rate law. Is it compatible with your data, your experimental data or reaction data? Okay. So before I go to the mechanism and rate limiting step, okay. So in order for you to to select a mechanism, okay, let's refer to your textbook. Okay. So when you go to this, all right. Okay, these are the 7 steps that we have reviewed last time. Okay, if you look at this, okay, the first 2 steps involving diffusion, right? So external diffusion and internal diffusion, right? Then only we go to adsorption. Okay, the third step, adsorption, reaction, and desorption. Okay, in this chapter, we assume that these first 2 steps, external diffusion and internal diffusion, is rapid. So we only consider the important steps in this chapter. The important steps are step 3, 4, 5, which is adsorption, surface reaction, and also desorption. Okay, so but in other 2 chapter after this, we will consider this external and internal diffusion, right? So these are the mechanisms. So these are so in the mechanism there are 7 important steps. Okay, so 3, 4, 5 is the one that we wanted to learn in this chapter, right? So if you refer to your textbook, okay, right. So it will go briefly on step 1. Okay, diffusion from the bulk to the external. Okay, so say the reaction is actually A producing B. Okay, always in this book they use reaction reactant A producing B. So here diffusion, if you learn back in your previous years in mass transfer, right? So you will see that AB is actually your concentration of A at the bulk. Okay, CAS is actually your concentration at the catalyst surface. So here, something like, okay, sorry, need to scroll down a bit. Okay, here. So this is the mass transfer, right? So this is your solid catalyst. Okay, can you see my arrow here? So you look where is your CAB. Okay, so this is what we call a boundary layer, a thin film, an imaginary layer just outside the catalyst surface. So have a thickness of del, right? So here is the del. So AB is actually concentration of A, reactant A at the bulk here. And then this is the solid catalyst. So A will travel from bulk to the surface and into the catalyst pores, okay, in order for the reaction to occur. Right. So when you wanted to describe the mass transfer here, so that's why they're using the rate. Okay, rate is actually Kc times Cab minus Cas. Okay, so Kc is actually a mass transfer coefficient. You will see this a lot in this chapter. Okay, Kc, right? So this is like the one that you learned before, right, in your mass transfer. Okay, so what is Kc? Kc also can be described as dAb over del. So I hope that you highlight these equations because this is very important. It will be used throughout CRE2. Okay, what is dAb is actually diffusion coefficient of your reactant A and also product B. So del is actually the thickness of your boundary layer, right? So later you will see that in order for efficient mass transfer, okay, you need to make the thickness of the boundary layer thinner, okay, so that better mass transfer occurs from for your reactant A to the catalyst surface, right? So actually the boundary layer, we can treat it as a resistant. So by having higher velocity, your del will be lower. Okay. So as a result, your there will be more efficient mass transfer or reactant A transfer to the catalyst surface. Right. So if you look at this graph, okay, this is the rate. Okay, overall rate. So we're talking on we're talking in terms of internal external diffusion just now. Okay, so overall rate, okay, so it depends on velocity and also catalyst particle diameter. Okay, dp is particle diameter or your catalyst diameter. So when you know when external diffusion is lower step, okay, so when you increase your velocity, so your overall rate will also increase until up to a certain point when when velocity no longer affecting the reaction rate, okay, or the mass transfer rate, okay. But it also but however, when you increase the dp, okay, it will decrease your overall rate. Okay, is inversely proportional to the velocity. Okay, all right. So that is external diffusion. Okay, the step 2 is internal diffusion. So remember, when you have, you see, you have to remember this diagram. So this part is discussing on the uh, external part. So now we are talking on the internal part. Okay, so in internal part, okay, you will see that, okay, there's a micropores in the solid catalyst. All right, so for the internal part, okay, so we only consider the rate is equals to KRCAS. Okay, so because CAS is actually the concentration at the surface of the catalyst. Later in the next chapter 3, you will see that the concentration of A in this porous catalyst is actually CAR. So CAS is bigger than CA, is describing this CA. Okay, so for this internal diffusion, you can see that the rate constant, which is this R, is describing the rate constant of the reaction. Okay, you see here, and overall R constant, and CAS is concentration of external surface. So if you look here, when you increase the dp, your reaction constant will go down. So it is inversely proportional. Okay, So in order for you to increase the reaction rate, you need to have smaller catalyst size. Okay. Okay, so if you refer back to this, okay, this diagram, okay, and then this statement, you see, in this chapter, you can see that, okay, we see that at small particle size, internal diffusion is no longer the slowest step. Okay, so in CRE2 or in the solid catalyst reaction, right? So deriving a rate law is actually based on the slowest step. Okay, so remember that 7 magical step. You need to know which one of these 7 among these 7 steps is the slowest step, right? So the one that have the slowest step is actually the step that we select to derive the rate law. Okay, it's not the fastest step. So that's why in this chapter, okay, we assume that the internal diffusion, external diffusion, which is step 1 and step 2, and also step 6 and 7 are the fastest or rapid step. Okay, so the one that the slowest step is either step 4, 5, 6, which is adsorption, surface reaction, and also your desorption. Okay, so this part. Okay, so let me scroll a bit here. So remember the 7 step. Okay, so now we are considering these 3, 4, 5 as one of the slowest steps. So it's either 3 or 4 or 5. Okay, either one. So this 1, 2, 6, 7 is in the chapter we treat it as a rapid step. Okay, so back to the internal diffusion just now. Okay, right. So here, okay, when you have a look on this one, okay, having smaller catalyst making the reaction even faster. Okay, so that's why we assume that in this chapter we use a small size of catalyst so that we can neglect the effect of internal diffusion or external diffusion. Right. So the next step is adsorption. Okay, so adsorption is due to two, physical adsorption and also chemisorption. So for in this case, normally we use chemisorption. Okay, so here if you see, this is the reactant A. This is what happened in step 4. So A will go to the catalyst active site. So S represent active site. Okay, so it will go to the active site and attach, making chemisorption. So it will become A dot S. So this step is a reversible process. All right, so it's something like this. Okay, so if you refer to my slide, okay, right, let's go to my slide. Okay, so if you refer here, okay, for reaction A to B, so this is how the mechanism would be. So A, in order for A to become B, so first it will go attach on the active site. So it become A dot S. Then only it will go to the surface reaction for A to convert to B. Okay. So it's either single site or dual site. Okay, so I will elaborate more about this. And then in this part, surface reaction, which is step 4, sorry. So then only A is converted to B, and then followed by B dot S, which is in desorption from surface. This is step 5, right? So for for reactants that we have more than one reactants and more than one product, so the surface reaction can be dual side or elite radial, and then desorption from surface. So you have to understand this term first. All right. Okay, so I think I will stop here for the first part of this chapter 1 part 3. So continue to the next part, which is that I will show you some example on producing the rate law. Okay.